All right, CHG 473. I'm sorry we don't have class today, but I do have a couple of homework hints for you. And so let's first start off with a couple of the basics, things that we talked about. So this gives the number average degree of polymerization in the absence of chain transfer. And so this is xn0 or x bar n0. So this zero, of course, means no chain transfer. And so if we look at this equation, we know or can figure out all of these variables. We can figure out what the monomer concentration is. We can figure out what the rate constants are. We can figure out what the initiator concentration is, the initiator efficiency, F, and we know something about Q as well, depending on what the termination looks like. So without chain transfer, we have a way to figure out what the degree of polymerization is. Now, when we have chain transfer, we know that x bar n 0 is greater than x bar n with chain transfer. And so we touched on the Mayo-Walling equation before the exam. And so when we have chain transfer, x bar n is less than x bar n not. And we had a clicker question on this last class as well. So the only time where we don't have a change in x bar n is when we have chain transfer to polymer. And notice here we have transfer constants, chain transfer to monomer, chain transfer to initiator, chain transfer to solvent. We don't have anything for the polymer or the polymer concentration in the Mayo-Walling equation because the polymer doesn't matter in determining x bar n for chain transfer. And so we derived this Mayo-Walling equation about a week and a half ago. And so I won't re-go through the derivation, but we're going to need this Mayo-Walling equation to determine what's happening with the degree of polymerization for our polymers when we have chain transfer. And so let's look at the homework. And we can talk through a couple of the key problems, and whatever we don't cover today, we can cover in class on Friday before the homework is due Friday at 11 p.m. So if we look at homework number 4 here, and I just broke out some of the problems in PowerPoint slides because it's easier to show. If we look at the first one, 4.4, calculate the concentration of benzoyl peroxide. So, and you know that peroxides are a radical initiator. And we're going to polymerize polystyrene with a number average molar mass of 750 kilogram per mole by bulk polymerization. So you have the molecular weight, and we know that bulk polymerization is only monomer, no solvent. So I tell you a little bit about how to figure out what the concentration of the monomer is. So we need concentration of monomer from the density. And remember, the units of concentration are moles per liter. So you have some unit conversion there to figure out what the concentration of monomer is. So we have the other parameters that we need. We have something about F, we've got the rate constants, and we have something about what the termination mechanism is. And so that should be pretty straightforward in terms of how to solve this problem. And notice, nothing is going on in terms of chain transfer. So you should know what the radical concentration is in the second part of the problem. Remember, that's m dot, and we have an expression for that in the notes. And the rate of bulk polymerization, remember, is RP. And so this problem is pretty straightforward. There's no chain transfer, so you should be able to use the tools that you know of already to solve this problem. Now, we contrast this when we go to the chain transfer problem. And so we have a similar expression of concentration. So remember that a decimeter cubed equals liter. And so this is in toluene, or this is methyl methacrylate in toluene. Oh, sorry about that. This is methyl methacrylate in toluene. And so you have to figure out what the concentration of monomer is using that information. And then we have calculate the initial rate of polymerization and the number average molar mass of polymethyl methacrylate. And so now we've got all of these chain transfer constants or chain transfer rate constants that we need to deal with using the Mayo-Walling equation or using the information that we have in the chain transfer slide. So this one will take some more work. I want you to look at this one today, turn it around, work on it a little bit as you're doing your homework today and tomorrow, and then ask questions on this on Friday. This one is a problem that we haven't done previously, and so you'll have to think about how to approach this problem in your homework. So this problem should be pretty straightforward. And so draw the mechanism for cationic polymerization of styrene using sulfuric acid as the initiator. And so we talked about ionic polymerization. So this will get you used to drawing some of those structures. And then this is a special living polymerization problem. We're going to be using sodium naphthalide as the initiator. And this is just in the next part of the notes in anionic polymerization. So this is anionic polymerization. And it's anionic polymerization of styrene. Again, you have some indications of what the rate coefficient is for propagation. We have an idea of what the concentration of monomer is and the concentration of initiator. However, this is a special case for living polymerization. So we've talked a little bit about anionic polymerization and what the mechanisms are, but we haven't covered living polymerization. So this is what I want to talk about on Friday. It's in the notes. I give you an example of sodium naphthalide polymerization in the notes, but this is something that you can read ahead on a little bit and start to figure out what is special about living anionic polymerization with sodium naphthalide and how you might approach the dispersity and the number average molar mass. And so the equations are pretty simple in this part. This is not a radical polymerization. This doesn't have anything to do with the more complicated expressions in the first two problems for X and naught. But when we have living anionic polymerization, we have a rather simple expression for X bar N. And so we'll talk about that on Friday, but this is something that you should be able to read ahead in the notes and take a look at to prepare for asking questions on Friday or during office hours. Finally, I did want to talk about this problem because this is basically the same as our chain transfer problem. However, what I want you to do is to make up a chain transfer strategy to obtain PMMA, and this gives you an idea of what the X bar N should be once you know the molecular weight and, of course, the M0. And so this is a little bit more open-ended. You can use some of the data from problem 4-5. So you can start with something like this, and then you really want to take a look at the chain transfer constants in the notes. And so you can borrow from the previous homework, or if you look at the Mayo-Walling equation, we'll go back to that. So if you look at the Mayo-Walling equation, there's all these transfer constants, right? And so we know the transfer constants, this Cm, Ci, and Cs, those are taken from the ratio of these transfer constants. So you want to look in the first problem, you want to look back and get an idea of how those transfer constants are formulated. But then we have a bunch of transfer constants here that we can use for our chain transfer strategy. So whether or not we add, say, a little chloroform, whether or not we use chain transfer to solvent. And so notice what the transfer constants are. They give us this transfer over Kp. So if you look back at how we derived the Mayo-Walling equation, you have Kp here, and you have the transfer constants here. So in the homework, I don't necessarily give you the transfer constants. I give you the rate constants themselves. And so you can come up with what Cm is in terms of the rate constants, or Ci or Cs. And so in this homework problem, I'm really looking for you to design a strategy. What are the concentrations? What's the solvent? Using a chain transfer strategy to come up with the target polymer. Come up with the target polymer, which is, if we just go back to the homework, this 50,000 grams per mole polymethyl methacrylate. And so again, you'll have to calculate X bar N0 in the absence of chain transfer. You want to calculate the X bar N when you do have chain transfer, and talk about how your chain transfer strategy lowers the X bar N0 in order to satisfy the conditions of this problem. So that's a little bit more open-ended, but you have some good hints and have practiced this in the chain transfer problem in problem 4.5. Okay, that should be everything. That's my hints on the homework. Of course, you are welcome to ask questions by email. I won't be in the office on Thursday, but I'll be in the office all Friday morning. Stop by before class or after class. I'm happy to do some office hours and make sure that everyone's in good shape for the homework. All right. Thank you very much.